Hello everyone, my name is Wenbin Yang. I'm research associate at the University of Stuttgart. It's a pleasure for me to present my research work within the framework of the Safe Barriers project today. My research work focuses on the development of MEMS sensor-based monitoring system, which will be applied to the engineered bentonite barriers in the underground radioactive waste disposal structure. First of all, I would like to make a brief introduction of the University of Strathclyde in which I'm working. The University of Strathclyde is located in Glasgow, Scotland. The university has the biggest engineering sector in Scotland. The Department of Civil and Environmental Engineering has three research groups, including the Engineering Geosciences and Geomechanics Group, the Environmental Research Group, and the Infrastructure Research Group. The head of department is Professor Rebecca Long. Then let me introduce the general background of the Safe Barriers project. The Safe Barriers project is a multidisciplinary EPSRC research program exploring the coupled thermal, hydraulic, mechanical, and chemical evolution of the bentonite barriers for the geological disposal of high-level radioactive waste. The project integrates a team of multidisciplinary researchers from 6 UK universities and the British Geological Survey. A key aspect of the project is to develop new monitoring technologies, which will be used both in laboratory experiments and at the field scale. From the picture on the left, we can see the cross-section of structures of the bentonite engineered barrier. The radioactive waste is stored inside the steel canister in the center, which is surrounded by bentonite blocks between the canister and the rock. The whole system is placed within the rock at 200 to 1,000 meters below the ground surface. The text shows the collaboration relationship between participants of the Safe Barriers project. Precisely, with regard to work package that I'm currently working on, the objective of our work package is to develop multi-sensor monitoring system to trace the spatial and temporal evolution of thermal hydromechanical variables such as temperature, relative humidity, pH value in the barrier at the laboratory scale and eventually at the field scale. The embedded MEMS sensors will be developed at Strathclyde to measure the thermal hydromechanical variables in the hydrated bentonite. The MEMS sensors will be validated and calibrated in conjunction with other monitoring facilities and techniques. Once tested, the MEMS sensors will be deployed for geomaterial experiments in other work packages. As you might not be familiar with the concept of MEMS sensors, here is some basic information. The term MEMS stands for microelectromechanical systems. The MEMS sensor converts physical quantities, such as temperature, pressure, and humidity, into electric signals in the form of voltage and current. In comparison with traditional sensors, the MEMS sensors deploy the same sensing principles as their microscopic counterparts, but the MEMS sensor has a miniaturized size in the order of micrometers and nanometers. Furthermore, the MEMS sensor can be easily integrated with other microelectronic functional blocks, such as the power supply, the sensor readout circuit, the analog digital converters, etc., on the same silicon substrate. There are different criteria of classification of the MEMS sensors. First of all, the sensors can be classified according to the sensing principle into different categories, including piezoresistive sensors, piezoelectric sensors, capacitive sensors, magnetic sensors, optoelectronic sensors, and so on. The sensors can also be classified by sensor structure. You see a few examples of the MEMS sensors in the following slide. The first example of the MEMS sensor is a piezoresistive cantilever relative humidity sensor. As you can see in the picture, a thin layer of hydrogel is deposited on the surface of the cantilever beam. As the hydrogel absorbs or dissolves water due to the humidity variation of the surrounding environment, the weight change of the hydrogel will cause the proportional bending of the beam, which leads to the axial stress along the beam to vary subsequently. The change of axial stress is then converted to electrical resistivity variation thanks to the piezoresistive structure at the clamping point. We can thus establish a mathematical relationship between the relative humidity and the resistance of the piezoresistive material. The microscopic photo of the cantilever beam can be seen in this picture on the left, from which we can see that the typical dimension of MEMS sensors is in the order of micrometers. The second example is diaphragm structured gas pressure sensor. Four piezoresistive sensors are deposited on the edge of a very thin diaphragm, covering the enclosed cavity beneath it. The air pressure inside the cavity can be considered to be constant. Here you can see the microscopic photo of the piezoresistive sensors on the diaphragm, as the picture on the bottom right. Upon the variation of the exterior gas pressure, the diaphragm will bend upwards or downwards subsequently, which will lead to a proportional change of the stress sustained by the piezoresistors. The four piezoresistors are connected in the Wheatstone bridge structure so that the resistance variation of the piezoresistive sensors is converted to a differential voltage output. In comparison with the traditional sensors, the major advantages of the MEMS sensors include the minimal power consumption in order of microvolts to millivolts, and the reduced sensor size in the order nanometers to micrometers. Furthermore, it's practical to integrate small integrated circuit components in conjunction with the sensor on the silicon substrate, and the batch fabrication of such system on chip is a very efficient way to produce a mass quantity of sensors in a single process. The major technical challenges for the monitoring of the engineered clay barrier include the following factors. First of all, as the gradient of thermohydromechanical variables can be very high in specific locations inside the bentonite barrier, as shown in this graph on the right, which presents the evolution of moisture content along the path A to A prime, it's important to reduce the dimension of the sensor as much as possible to measure the thermohydromechanical variable at a precise location. Secondly, as you can see in this view figure, the long-term offset of the sensor and the cross-interference of some variables could also compromise the accuracy of the sensor. Therefore, the compensation and calibration techniques should be developed in order to improve the long-term accuracy of the sensors. In the context of the laboratory experiments of the Safe Barriers project, the sensors will be installed in an experimental bentonite block, so the sensor size must be reduced to minimum in order to minimize its influence on the hydromechanical response of bentonite. The reduced sensor size will also enable the sensor to measure the high gradients of thermohydromechanical variables and to minimize the temperature gradient effect on the accuracy of the sensor. From these photos, you can see that our sensor board is significantly smaller than the typical temperature sensor. At this stage, our design uses wired connection between the sensors and the control system for fast and reliable signal transmission, while a wireless communication module is in our long-term plan. In the perspective of the application of sensors in the field repository, the sensor size is no longer a major restraint. In the contrary, the wires of the sensors increase significantly the complexity of the bentonite heating process, as you can see in this picture. Therefore, it is essential to establish a reliable wireless communication with the sensors in order to eliminate possible preferential paths for radionuclide migration. Furthermore, low power consumption of the sensor is necessary to ensure the long-term performance of the monitoring system during the life cycle of the engineered barrier, as the replacement of power source is extremely difficult to achieve. In the end, the embedded sensors should be mechanical and thermally robust so that the sensors can sustain the harsh working environment inside the bentonite barrier. The first prototype of the MEMS sensor monitoring system has been implemented on the printed circuit board. We have chosen the state-of-the-art commercial MEMS sensors on the high end of the market, as commercial sensors have better signal stability and precision than laboratory fabricated MEMS sensors. The wired data communication is adopted for laboratory experimental tests in order to reduce the size of the sensor block to the minimum. The commercial relative humidity sensors are less accurate for the high relative humidity range, so we are also planning to develop a new MEMS relative humidity sensor via the micromachining process in cleanroom, which is dedicated to the high relative humidity range measurement. In this slide, you can see the configuration of the sensor monitoring system. On the left is a controller board which controls the communication with the sensors connected to it and sends the information acquired from the sensors to the user PC for later registration. One controller board can pair with 8 sensors at the same time. Here you can see the different functional components in this rectangle. And on the right is a single sensor board which has a typical dimension of 1 square centimeter. The sensors are connected to the controller board via the wires, as you can see in this photo. In this figure, you can see the design diagram of the sensor monitoring system. Different types of digital sensors can be integrated to a single controller board using the same serial communication protocol. The controller board then communicates with the user computer interface via the RS-232 serial port. The real-time measurement results can be visualized in the user interface and then registered in a file in the hard disk. This picture demonstrates the user interface constructed in the lab view environment. The section on the left indicates the status of serial communication between the controller board and the PC. The section at the top right is used to select activated the sensors and set the measurement period. The second at the bottom right shows the real-time measurement results required by different sensors. As the MEMS sensors will be exposed to relatively high temperature and humidity of their working environment in the geological disposal structure, it is essential to encapsulate the sensors so as to protect them from exterior humidity, mechanical shock, and chemical corrosion. 2 encapsulation methods have been tested in comparison. The first method is called conformal coating by spraying aerosol to cover the PCB circuit with lacquer. This technique is sufficient for the waterproofing of circuit boards for a period of several days. A long-term solution for the encapsulation of sensors is called the potting technique. The circuit board is submerged in polymer resin compound inside a small potting box. After the hardening process of the polymer resin, the sensor is buried in the center of the polymer block. The criteria for polymer resin selection include good thermal conductivity and electrical insulation, sufficient mechanical strength, and high working temperature. Based on the criteria mentioned in the previous slide, we have chosen 2 polymer compounds, epoxy and polyurethane, for our encapsulation experiment. You can see a brief summary of the coating procedure here. The photo below illustrates three stages of the sensor board encapsulation. The initial PCB board on the right, the relative humidity sensor covered by a filter cap in the middle, and the encapsulated sensor block on the left. The encapsulated sensor block is slightly bigger than its prototype, but the sensor is better protected from moisture, mechanical impact, and chemical corrosion. In the case of the relative humidity sensor, the Sensarin SHT25, we have adopted the filter cap fabricated by the sensor supplier to protect the sensing area from direct contact with water, dust, and other contaminants. The filter cap allows the propagation of water molecules to the sensing surface, but filters out all particles whose dimension is superior to 0.1 micrometer. The photo and schematic of the filter cap can be seen in the picture below. The encapsulated and non-encapsulated sensors have been tested in various testing environments. The first validation test of the relative humidity sensor is proceeded in enclosed containers above saturated salt solutions. The relative humidity above saturated solutions is considered as a constant relative humidity reference point, thus can be used to evaluate the measurement accuracy of the relative humidity sensors. The chemical solutions and their corresponding relative humidity levels are listed in the table on the right. The photo on the left shows the experimental setup of the sensors installed above the saturated solution and connected to the controller board outside the container. This figure shows the short-term evolution of the relative humidity levels above three saturated solutions. After closing the container, the equilibrium of relative humidity is achieved in around 2 hours. We can also observe that in high relative humidity environments, there is a slow deviation of measured relative humidity above the theoretical value as time goes by. This offset of 3% approximately is coherent with the observations by the supplier of the sensor. This figure demonstrates the long-term temporal evolution of the relative humidity for an extended period of 7 days. The relative humidity values are the calculated average of measurements taken in the same day. It can be seen that once the equilibrium is attained, the sensor readings are relatively consistent over the entire experiment period, with discrepancies inferior to 1%. As a conclusion of the first experiment, the relative humidity sensor is most accurate between 10% and 80%, with an error margin of less than 2%. As the relative humidity increases, the offset increases correspondingly, and for the relative humidity over 90%, the error margin is between 5% and 8%. That's the field that we'll focus on improving in our future work. The sensors all showed good temporal stability over a period of 7 days. In the containers where the relative humidity is high, an offset of at least 3% has been observed after 6 to 8 hours of measurement time. The performance of relative humidity sensors in higher temperatures is currently under investigation. In the case of the relative humidity sensor, the Sensarin SHT25, we have adopted the filter cap fabricated by the sensor supplier to protect the sensing area from direct contact with water, dust, and other contaminants. The filter cap allows the propagation of water molecules to the sensing surface, but filters out all particles whose dimension is superior to 0.1 micrometer. The photo and schematic of the filter cap can be seen in the picture below. This figure demonstrates the temperature measured inside the climatic chamber, where the interior temperature drops gradually from 120 degrees to room temperature. Full temperature sensors and the high-precision platinum resistance thermometers are installed inside the chamber. The measurement of temperature using both instruments is synchronized, and the measurement results are compared. In the figure, we can see that the temperature measured by the sensors and the PRT probe are in full agreement, and the discrepancy is below 0.5%. For temperature between 100 degrees and 120 degrees, the discrepancy between different instruments increases to less than 2%. The same experimental setup has been used to compare the relative humidity inside the chamber measured by different sensing instruments. Four relative humidity sensors, together with the Vaisala relative humidity probe, are installed inside the chamber, and the relative humidity level inside the chamber are imposed as increasing and decreasing steps from 30% to 90% and then back to 30%. From this figure, we can see that the relative humidity measured by four sensors and the reference probe are quite coherent during the increasing cycle of the relative humidity, while the discrepancy is higher for the decreasing cycle after the long exposure of relative humidity sensors to a humid environment. In the perspective of the application of sensors in the field repository, the sensor size is no longer a major restraint. In the contrary, the wires of the sensors increase significantly the complexity of the bentonite heating process, as you can see in this picture. Therefore, it is essential to establish the reliable wireless communication with the sensors in order to eliminate possible preferential paths for radionuclide migration. Furthermore, low power consumption of the sensor is necessary to ensure the long-term performance of the monitoring system during the life cycle of the engineered barrier, as the replacement of power source is extremely difficult to achieve. In the end, the embedded sensors should be mechanical and thermally robust, so that's the presentation of my research work for today, and thank you very much for your kind attention.